Hi everybody, in this video I'm going to go over a review of solving conservation of energy problems. In these situations we're given a scenario where energy is transformed from one type of energy to another, and then you're asked to calculate something about it. So we're going to go through three or four examples here, and in each case we're going to look at the system, we're going to do a sketch before and after, a bar chart, and then solve mathematically. Let's get started. So our first scenario here is we have if a volcano can spew a 500 kilogram rock vertically upward a distance of 300 meters, what was its velocity when it left the volcano? So let's do a sketch here. So we have a volcano and it launches a rock out, so it gives it some sort of speed, and then it reaches a maximum height. So here's my volcano, here's my rock that's moving up. And then after, here's my rock at its maximum height. I also always want to put my lowest point as my 0 reference level, so I'm going to set that here. Okay. And let's also make a list of the variables we're given here. So we know that the mass is 500 kilograms. We know that, we don't know that initial velocity, that's what we're looking for, but we know the height is 300 meters. Okay. So let's look at what our system is. I'm going to include the rock, I'm going to include the volcano, and I'm going to include, spell volcano wrong, the earth. Okay? All right, so now let's take a look at our bar chart. So we want to figure out the type of energy that this rock volcano system has before and after. So initially it is moving, so we know it has some kinetic energy. It does not have any gravitational because it's at our 0 point. There's no springs or rubber bands or anything stretching or compressing, so I'm going to put 0 for elastic. There's no external force, right? I included the volcano in the system because there's no external force. I want the volcano to be within my system. So there will be no work. After it reaches this maximum height. Now, something to remember, we learned this a while ago, but when something is at its maximum height, its velocity equals 0 for a very short amount of time before it starts moving down. So we're looking at that point. So whenever we see a maximum height, you know the velocity is going to be 0, so it's going to have 0 kinetic energy. But it does have gravitational potential energy because it's above my 0 reference level. There's still no elastic because there's no elastic object stretching or compressing, and there's no internal. So here's my completed bar chart. Now, I want to make an equation based on this bar chart. So I'm going to say, okay, I have kinetic plus 0 plus 0 plus 0 equals 0 plus gravitational plus 0 plus 0. So this is the equation I made based on my bar chart. So now I can simplify this to just kinetic equals gravitational. Now, if you look back at your notes, we know our equation for kinetic is 1/2 mass times velocity squared, and our equation for gravitational is mgh, mass times g, which is 9.8, times the height. So what I'm going to do now is I'm going to plug in those mini equations into our equation we just made. So now I'm going to have 1/2 mass times velocity squared equals mass times g times the height. Okay? And all I did was first I needed to figure out that bar chart and figure out what type of energy we had before and after to make that equation, and then I plugged in my mini equations. Okay, so now let's take a second to plug in our numbers. So I know my mass is 500 kilograms. So I'm going to say 1/2 times 500, and I don't know my velocity, so I'm leaving that as v squared. My mass again is 500, g is always 9.8, and I know my height is 300 meters. So now this is just a math problem that we're going to solve. So we want to first put this whole thing in our calculator, and we're going to get 500 times 9.8 times 300, and that gives me 1470000. And then if I put 1/2 times 500 in a calculator, I would get 250 times v squared equals 1470000. Now I'm going to divide both sides by 250. to get that v squared alone. And I get v squared equals 5,880. Now, last step here, to get rid of that squared, we have to take the square root on both sides. And when I put that in my calculator, I get a velocity of 76.7 meters per second. And that's going to be my final answer. So this is the process we went through. We did our sketch for before and after. We identified our system. We wrote down the numbers we were given. And then we went through before and after all the types of energy and figured out what kind of energy it had before, what kind of energy it had after. Then we made an equation based on that, plugged in our numbers, and solved. Let's look at a second scenario here. We have Janseli is driving a 2,000 kilogram Volkswagen Beetle at 20 meters per second, and then takes her foot off the gas pedal. The car eventually stops due to effective frictional force of the axles, air, and other things exerted on the car. If the frictional force has an average magnitude of 1,000 newtons, how far will the car move before stopping? Okay, let's draw our sketch. So initially, we have a car, and it's moving. And then after, we have a car, and it's no longer moving. Okay? We know that the mass of the car is 2,000 kilograms. We know its starting velocity is 20 meters per second. We know there's some kind of force of 1,000 newtons exerted on it that slows it down, but we don't know the distance it travels. Okay? For our system, we're going to include the car, and we're going to include the Earth. Now, we have a force given to us, right? And it says it's the force of the axles, the air, and other things. So that means I'm not going to include any of those things in my system, because if I'm given a force, that means I can calculate work. So any object that might do work, like the ground, the axles, the air, I'm not going to include in my system. So my system is just going to be the car and the Earth. All right, now let's make our bar chart. So starting out here, the car is moving, so it has kinetic energy. I forgot to put my 0 point, but let's make it here. We notice that there's no change in the height of the car. It doesn't go up a hill or down a hill or something like that. So there's not going to be any gravitational potential energy. There's no elastic potential energy because there's nothing elastic, stretching, or compressing. But we know there is going to be work because there's a force done on it. Now, we need to decide, is our work going to be positive or negative? Well, we know it's slowing down our car. So if it's slowing down our car, the car is moving in, let's say, the positive direction, and that force is going to be in the negative direction. So we're going to have negative work. Okay, we know this because it is slowing down the car, it's decreasing the car's energy, and it's in the opposite direction. The force is in the opposite direction as the motion of the car. So let's make that work negative. Now after the car stops, due to that frictional force, it's not moving, so it has no kinetic. It still hasn't moved up or down, so there's no gravitational. There's no elastic because nothing elastic stretches or compresses. And we're putting no internal energy. Now, if we included like the ground or other things that exerted a frictional force in our system, then we would have internal energy. But it's going to be easier to just not include that in our system and then say it all does work. So that's why I did that here. So now based on this bar chart, we can have our equation kinetic plus 0 minus work. Notice I make it negative. Equals 0 plus 0 plus 0 plus 0. And we can simplify this to kinetic minus work equals 0. Now again, looking back to our notes, we know kinetic energy is 1/2 mass times velocity squared, and we know work is force times displacement. So I'm going to plug in those. So I have 1/2 mass times velocity squared minus force times displacement equals 0. Now, I know from my algebra that it's going to be easier to just move over that force times displacement. So I'll have 1/2 mass times velocity squared equals force times displacement. That makes it positive. And now I can start plugging in my numbers. So I know my mass is 2,000 kilograms. So 1/2 times 2,000. times, do I know my velocity? Yes, I do. It's 20 meters per second. Don't forget to square it. Equals my force, which I know is 1,000 newtons, times my displacement, which I don't know, so I'm going to leave it as d. So now I'm going to try and solve for d. So I'm putting this whole side in my calculator. So I have 0.5 times 2,000 times 20 squared, and I get 4, 1, 2, 3, 4, 5 zeros equals 1,000 d. Divide both sides by 1,000. And I end up with a distance of 400 meters. And that's going to be my final answer. Okay. All right, we are going to look at one more final scenario here together. Here we have a popular new spring hockey game that Steven got for his birthday uses springs to move a 0.0030 kilogram puck. It works like a regular hockey table, but instead of hitting a puck, the players use small springs. Each spring has a 120 Newton per meter spring constant and can be compressed up to 0.02 meters. How fast does the puck move when it departs from a spring that was initially compressed this distance? So let's make our sketch. So before, we have our puck is compressing a spring. And then after, our spring is no longer compressed and our puck is moving. Okay. So our system, we're going to include our puck. We're going to include the spring. We always include the earth. And I'm also going to include the table here just because I don't want there to be any work. So I like to include the surface most of the time unless I know that the surface is doing work and I have a force given to me. Okay, so let's look together at our bar chart here. Actually, let's start by making a list of what we're given. We know our mass is 0.003 kilograms. And we know the spring constant is 120 newtons per meter. And we know it's compressed 0.020 meters. And we don't know the velocity after, right? It says how fast. Okay, let's look at this bar chart here. So we have initially, it is not moving. Okay, it's compressing that spring, but initially it is not moving. I'm gonna make my 0 point here. And again, it doesn't move up or down. There's no change in the height, so there's going to be 0 gravitational potential energy. But there definitely is elastic, right? There definitely is elastic potential energy because that spring is compressed. There's not going to be any work because there's no external force exerted on our system. I included my spring, so there's nothing external exerting a force on the puck. Okay? Then after, it says the puck is moving, so we know it has kinetic energy. It has no gravitational because, again, it's not moving up or down. And at this point, it no longer has any elastic because the spring is no longer compressed, okay? We only have elastic potential energy when the spring is compressed. When it's at like its relaxed neutral state, it doesn't have any elastic potential energy anymore. So that's why I'm putting a 0 there. And there's nothing warming up. We don't have any significant frictional force. So I'm going to put 0 for internal. So here's my bar chart. Now let's make our equation. We have 0 plus 0 plus US, elastic, plus 0 equals kinetic, plus 0 plus 0 plus 0, which we can simplify to elastic equals kinetic. And again, if we remember, our equation for elastic is 1/2 kx squared. And our equation for kinetic is 1/2 mass times velocity squared. And we're going to plug in those equations for our equation we just made based on our bar chart. And we get 1/2 kx squared equals 1/2 mv squared. And now we can start putting in our numbers. So k is my spring constant, which is 120. X is how far it is stretched or compressed, which is 0.02. Don't forget to square it. Then I equals 1/2. My mass is 0.003. And I don't know my velocity. So let's start by putting this whole thing in my calculator. So I'm going to do 1/2 times 120 times 0.02 squared. And I get 0.024 equals, and then if I do 1/2 times 0.003 in my calculator, I get 0.015 v squared. I'm going to divide both sides by 0.015. Okay. And now I'm going to get 1.6 equals v squared. I'm going to take the square root of both sides to get rid of that squared. Square root of 1.6 gives me a velocity of 1.3 meters per second. And that's going to be my final answer. Okay. Okay, let's look at one more problem together. So here we have a 0.3 kilogram ball is dropped from resting from a height of 8 meters. It falls and compresses a spring with a spring constant of 80 newtons per meter. The spring is compressed 0.2 meters. What will the ball's velocity be? Okay, so let's sketch our situation. And before we have a ball and it's up at a height, and there's a spring below. And then after it has fallen off and it has compressed our spring. Okay. I'm going to put my 0 at this point where the ball is at its lowest point. And now looking at what is my system. So I'm going to include the ball. I'm going to include the spring. And I always want to include the earth. Okay. Now let's make a list of what we're given. We know the mass of the ball is 0.3 kilograms. We know its original height is 8 meters. And we know the spring constant here is 80 newtons per meter. And it compresses it 0.2 meters, and we don't know the velocity. Okay. All right, let's take a look at our bar chart now. So looking originally, it is not moving, it's at rest, so it has no kinetic energy. It is above our 0 point, so we know that it must have some gravitational potential energy. At this point, it has not yet compressed the spring. So just because there's a spring in your system doesn't mean it always has elastic potential energy. When it is not stretched or compressed, it does not have any elastic potential energy. So in this case, before the ball compresses it, it has no elastic potential energy. There's nothing external to our system doing work, right? So there's no force exerted on our system, so there's 0 work. And then after, we said it's still moving, right? It asks how fast it's moving. So it has some kinetic. It has no gravitational because it's now at the lowest point, okay? And again, we can set our 0 wherever we want. So I like to set my 0 at the lowest possible point. It definitely has elastic because it compresses that spring. And there's no internal because there's nothing warming up or deforming. So here's our bar chart. Now let's make an equation based on that. And we have 0 plus UG plus 0 plus 0 equals kinetic plus 0 plus US plus 0. And we can simplify this to UG equals kinetic plus US. And looking back at our equations, we know kinetic is 1/2 mass times velocity squared. UG is mgh. And US is 1/2 kx squared. So let's plug in this for UG, this for K, and this for US. And we get mgh equals 1/2 mv squared plus 1/2 kx squared. Okay. And now we can start plugging in our numbers. So we know our mass is 0.3. So 0.3, g is always 9.8. We know the height is 8 meters. Okay, equals 1/2. Mass is still 0.3. We don't know our velocity, so I'm leaving it as v. plus 1/2. We know our spring constant is 80 and it's compressed 0.2 meters. Okay. Now I'm going to put this whole chunk in my calculator and I get 23.5. Half of 0.3 is 0.15 v squared. Plus, put this all in my calculator, 1/2 times 80 times 0.2 squared is 1.6. Now, next thing I want to do is subtract my 1.6 from both sides, and I get 21.9 equals 0.15 v squared. And I'm going to divide both sides by 0.15. And I'm going to get 146 equals v squared. And our last step here is to take the square root. And I get square root of 146 gives me a velocity of 12 meters per second. And that is my final answer. Okay? So in this video, we went over 4 different scenarios where you have some sort of energy transition. We have to read the problem, interpret what does it look like before and after, make a list of the variables we're given. Then we're going to make a list of our system, including all of the objects involved. We always include the Earth. And when we are given a force, we don't include the object that exerts that force, right? Because we want that to do work. Then we made a bar chart based on the scenario. We made an equation based on the bar chart. We plug in our small equations to the equation we just made, put in our numbers, and then solve. Hopefully this video was helpful for you. If you have any questions, you can always email me. Have a wonderful day.